we're here to talk about. And part of this, again, is understanding first how to describe motion. Now, that sounds simple. Things move. It's easy to describe. It moves from here to there. Well, it turns out it's not so simple. Let me introduce you to a couple of folks. Galileo, you've probably heard of these people. Galileo and Newton. This is, of course, what Newton's laws are named after. But part of the reason I'm bringing these folks up, and there are only two of many, many, many. Newton gets all the credit. He would be the first to tell you that he based, his laws of motion are based off of literally thousands, going back 1,000, 1,500 years, 2,000 years back to Aristotle. Many, many years of many smart people thinking about this. So even though this is a simple concept, we're dealing with a very simple thing tonight, forces in motion. One of the things you should keep in mind while you're struggling with some of these concepts is that it took many, many, many centuries for the smartest people in the world to figure this out, the very simplest first step. Okay? So it isn't simple. It's hard. It's very, very hard, actually. But in another way, it's simple. I mean, we've kind of, what Newton helped us understand is that there's some very simple laws that can describe it. Galileo really helped us begin to understand how to describe motion. I keep on saying describe motion. And what I mean by that is how we define velocity and acceleration, which are actually not very easy concepts for a lot of people. Okay? For starting out. If you're just starting from scratch, these are complicated concepts. And then Newton came along and figured out how to, he basically came up with this idea of force. There really was no force before Newton. I mean, there was no concept of force before Newton. And, he was a pretty smart guy. I mean, this is my point, is that it took, this guy was kind of a freak of nature. He was really a smart guy. He invented calculus in order to describe the motions of the planets. So this is laws of motion are simple when laid out, but I just wanted to point out that it's understandable. You should feel that it's reasonable if you struggle with some of these concepts. Okay, so there's three laws. There's a lot of different ways of describing these laws. But really there's three different laws, and one way of describing them is that there's a law of inertia, which is really just explaining that there's this thing called inertia, this tendency of an object to stay in motion. There's the law of force and acceleration. This is really where the mathematics, where the description of how forces in motion relate to each other. And there's a fairly famous law that you probably all know, the law, or you're familiar with the language of it, action and reaction. Every force has an equal and opposite reaction force. So these are the three laws. We're going to talk about them in more detail now. And I've got some animations that are okay, so the first law, and unfortunately it's hard to do this without putting a bunch of words up here. Let me say it too, I don't want people necessarily have to copy this stuff down. You'll get access to this PowerPoint. Is that correct? We'll send this PowerPoint out.
Yeah. I haven't seen your last one, but you, I did. Jennifer to send down. Okay.
So this is sort of an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted on by an outside force. So there's a whole bunch of language here, and the language is actually very specific, and I don't want to go into parsing this language, but essentially what this says is that an object that's at rest isn't going to change its state unless there's an outside force that acts on it. The outside part's important, and it seems simple, but you have to keep them. There's often internal forces. All right, let me give you a very simple example. Can I pull myself above the floor? All right. Why that's the case isn't real simple. You should think about why that's the case. But the simple answer is that there's no external force. All the forces are internal. My shirt pulling on my hand just as much as my hand pulling on my shirt. Okay? So an object at rest tends to stay at rest unless acted on by an outside force, and an object in uniform motion. What do we think that means? Okay. Well, A constant acceleration would be a little different, although that is a uniform motion in a sense, but this means, so so it is kind of sneaky language. It's not necessarily well defined. What uniform motion means in this case is a constant velocity, which means constant speed in a particular direction in a straight line. Okay? Let me use something. Okay, so my fun animation here, let's see how it goes. Okay, object in uniform motion tends to stay in uniform motion. Straight motion in a straight line. Okay? Okay, Newton's second law of motion. Okay, this gets a little bit more complicated. This is the law, for those of you that sort of, if you're getting up into sort of middle school and high school, you start dealing with the F equals ma. But let me not intimidate anybody, or let's not get to the mathematics yet. All this is all it's saying is that if there is a net force on an object, that object will accelerate. That's all that it's saying. So let's just keep it at the simplest level first. If an object has a net force on it, it will accelerate. Let me add one more part to it, in the direction of the force. Okay? So when we can get to a slightly more complex way of looking at this, acceleration is higher with higher force. That seems obvious. The higher the force, the greater the acceleration. And then the acceleration is lower with higher mass. So the bigger the object, given some force, it won't go as fast. Okay, so what do we mean by net force? That's a word that's a phrase I used in there, but what does that mean? Yeah?
Force taking into consideration all other forces and their directions?
Absolutely. So in most situations, there's not just one force, there's a bunch of forces on an object. You have to take into account all of those forces. It's very rare, it's a very rare situation. As a matter of fact, in the world we live in, there's really no circumstance where there would be no force on an object. I mean, there's always gravities, always being applied. But there's also other objects, like we talked about last time. Is this object accelerating? Okay. Does that mean that there's no force on it?
Normal force is up from the table.
But the fact that it's not moving, what does that tell us?
Forces from all the directions.
Right. All the forces are balanced. The net force is zero. The net force is zero. Okay. So all the forces add up together to give you zero force. Okay. But that doesn't mean that there's identically near zero. It means that there's opposing forces. It could be forces coming from all different directions. Okay. There could be 3 forces, 4 forces, 10 forces on an object. Okay. This is what I just described. Okay, so we got ahead of ourselves a little bit. If we have an object sitting on a table, are there forces on the ball? You guys all just answered that exactly correctly. Yes, there are forces on the ball. And what's the net force on the ball? It's not moving. Right. So that's what net force means. You guys got the concept. Net force is the word for the total adding all the forces together. So here's a quiz. So we're going to do this quiz, Newton's laws of motion. So what I've got, for those of you who can't see this real well, this is helping you get a little bit more of a sense of the quantitative aspect of Newton's second law, which is force equals mass times acceleration. So, and it's an intuitive law. You kind of, let me describe the quiz I'm giving you here. I've got a big force on a big mass, a big force on a small mass, a small force on a big mass, and a small force on a small mass. So everybody got that? So what's going to happen when I say go here? I mean, what's generally going to happen?
Big force on small mass.
They're going to shoot.
So has everybody got a predict? They're very predicting. You can probably predict. I kind of heard a bunch of things.
The small force on the big mass is
So Small force on the big mass is what?
Losers.
And what's the winner?
Big force on the smaller side.
All right. Now, of course, this is all happening in PowerPoint. It's not really physics, but that's what you guys got it right. Now, the other two are hard to predict because it kind of depends on how big the mass is and how big the force is. They actually can be in either order. Okay. Okay, great. So this is good. So this is all that the second law is saying. All the second law is saying is that there is a proportionality between force and acceleration. Okay, that how fast you accelerate if you have a net force has to do is related to this thing called mass. Okay. Okay, the third law. Now, the third law sounds really simple, and it is simple in a way. But all of these laws are, you have to be careful. Now, for the most part, the way you're going to be describing, especially in elementary, if you're talking about first, second, third grade, you're going to want to keep this at the simplest level, but you do want to be careful about how you apply. There are specific ways in which you need to apply these laws. Like, for example, for the second law, when we say net force, we have to be very specific about what we mean. You have to. So here's how we do it. Here's how I teach undergraduates. You have to choose the system. You have to be very specific. My system is this object, not the object in the table. Because if we talk about the object in the table, things get more complicated because then there's the force of the. Okay, so you have to be very specific about what object you're talking about when you say net force. You see what I'm saying? What is the object that we're figuring out what the net forces are? If you're fuzzy about that, then things will get confusing. Okay. Same way with this law. You have to be very careful about which thing you're talking about. You have to, what I have students do is you actually draw a picture and draw a circle around which thing you're talking about before you use any of the equations. And I know we're not going to be using equations. You certainly aren't going to be using equations for the younger kids. But even drawing pictures and thinking about forces, you want to make sure you define what object you're talking about, or a combination of objects. So Newton's third law, and I know you can't read this from the back, but it's basically saying when one object applies a force to another, when one object applies a force to a second, the second is applying an equal and opposite force back on the first. That's always true, and it sounds simple, but it can sometimes be confusing. Okay? So this object, so what have I drawn here? This force pointing down. What object is applying that force? Wait, somebody said gravity, and that's an interesting answer because in a way that force originally comes from gravity. But the way I would say is that gravity is applying the force to the ball, and in turn the ball is applying that force to the table. So that answer is right in a way, but you want to be careful. So yes, the ball is applying the force to the table downward. Now where's the equal and opposite force? Right, so drawing pictures like this with these two arrows, I think, so this is what I mean. If you were going to draw a picture of the forces on the ball, this would be one of them. And what would the other force be on this ball? Well, friction. What's the other force on this ball? Why isn't it moving? If there's a force upward, why isn't it going?
Gravity.